Have you ever wondered what it's really like to stare down a university chemistry final? Well, we got our hands on one and we're jumping right into the deep end with one of the toughest questions, question 6. But here's the thing, there's a really cool twist to this one. Okay, let's get into it. You know, an exam like this isn't just about memorizing formulas and getting the right answer. It's about learning to think like a chemist, to see the world their way, and to decode the hidden rules that run everything, all wrapped up in one single problem. And here is that twist I mentioned. It turns out the university handed out two different versions of the exam. So for some students, question 6 was all about invisible gases finding this delicate, perfect balance. But for the others, their question 6 was about the slow, unstoppable chemistry of rust. We're going to break down both of them and see what they're really all about. Okay, first up, challenge number 1, chemical equilibrium. This is all about how chemical reactions are kind of like a seesaw, you know? They're always trying to find that perfect natural balance point. So this table has all the key data for the first version of question 6. We've got two different reactions going on. In the first one, ammonia is breaking down into nitrogen and hydrogen. In the second, sulfur dioxide and oxygen are teaming up to make sulfur trioxide. The big idea here is that reactions aren't a one-way street. They go forwards and they go backwards until they hit the stable state we call equilibrium. This table is basically a snapshot of what things looked like before and after they found that balance. So, how do you measure that balance point? Well, chemists have this incredibly powerful number called the equilibrium constant, or just K. Think of K as the reaction's final score. It tells you, when all is said and done, did we end up with a ton of products, or did the reaction just kind of fizzle out? And this is where that one little number tells a huge story. For that sulfur trioxide reaction, the K value is massive, 30,000. That means the reaction just loves making products. The seesaw is slammed all the way to one side. But for the ammonia reaction, the K value is tiny. I mean, look at all those zeros. That reaction barely moves. The seesaw is pretty much stuck on the reactant side. So this one number, K, tells you the fate of the whole reaction. It's amazing. But hey, crunching numbers is only half the battle. This exam also wanted to see if students could read the story of a reaction unfolding over time just by looking at a graph. And here it is. This is that story, drawn out for us. You've got the amount of each chemical going up the side and time passing along the bottom. One line starts way up high and then drops. The other starts at 0 and climbs. The puzzle for the students was simple. Which line is which chemical? Honestly, the logic here is pretty straightforward when you think about it. Products are the things you make, right? So you have to start with none of them. Their line has to start at 0 and go up. So boom, that rising red line must be our product, sulfur trioxide. And reactants, those are the ingredients you use up, so their line has to start high and go down. That makes the falling blue line our reactant, sulfur dioxide. See, that simple graph tells a whole dynamic story. But wait a second, the recipe for this reaction used sulfur dioxide and oxygen. So where's the oxygen on this graph? Well, the students had to draw it in themselves. We know oxygen is a reactant, so its line also has to start high and go down. But here's the key. If you look at the reaction, you use 2 SO2 molecules for every 1 O2. That means the SO2 gets used up twice as fast. So the oxygen curve would fall, sure, but way more slowly than the blue line. Okay, deep breath. We're about to do a complete 180. Because for a whole other group of students, question 6 had nothing to do with invisible gases. Their question was about something you can see and touch, the slow, relentless, unstoppable force of rust. So, challenge number 2 throws us right into the world of electrochemistry. And really, this is all about the movement of electrons, these tiny, tiny particles that can either power a battery or totally destroy a piece of metal. So, the question sets up this little puzzle with 3 different situations. Scenario A, an iron nail all by itself in a vacuum. Scenario B, an iron nail sitting in some acidic water with oxygen around. And then scenario C, the really interesting one, an iron nail that's been coated in copper, also in acidic water. The big question is, which one of these is going to rust? And more importantly, why? Now, to figure this out, we need to look at this table. I know, it looks super technical, but it's actually pretty simple. It's just a ranking of how badly different things want to steal electrons. A big positive number, like the one for oxygen, means it's an absolute electron bully. It will grab them from anyone. A negative number, like iron's, means it's a total pushover. It gives its electrons away super easily. And rust? Rust is just this epic battle for electrons.
So let's look at what happens. In a vacuum, there's no oxygen, no water, nothing to fight with. So no rust. Easy. But in scenario B, now you've got the electron bully, oxygen, in the same place as the pushover iron. It's not a fair fight at all. That oxygen, with its super high positive number, just rips the electrons right off the iron. That whole process is what we call oxidation. And when it happens to iron, we call it rust.
And now for the big twist. You would think that coating the iron nail in copper would protect it, right? Nope. It actually makes it rust even faster. How is that possible? Well, the copper is tougher than iron, but it's still no match for that oxygen bully. So the oxygen steals electrons from the copper, and then the copper turns right around and steals replacement electrons from the iron underneath it. The copper basically becomes a middleman, making it even easier for the iron to fall apart. It's wild. It's actually why big ships have blocks of zinc attached to them. Zinc is an even bigger pushover than iron, so it rusts away first to protect the steel.
But this question wasn't done yet. It didn't just stop with rust. It took that same basic idea, the behavior of electrons, and connected it to the amazing world of molecular color and shape. The last part of the question asked why a certain zinc compound is colorless. Well, the color you see in these kinds of molecules comes from their electrons jumping between different energy levels when light hits them. They absorb one color of light to make the jump, and we see whatever colors are left over. But with this zinc complex, look at the diagram. All of its electron energy levels are completely full. Think of it like a bookshelf where every single shelf is totally packed with books. There's nowhere for any book to move. Since the electrons have no room to jump, no light gets absorbed, and so we see no color. It's just clear. Finally, students had to build a molecule with one of those ridiculously long chemical names. But really, it's just like building with Legos. You start with your main piece in the middle, the titanium atom. Then you start clicking on the other pieces around it, the ligands. Once you've built your positive titanium structure and your negative zinc structure, you just snap them together. It turns a name that's impossible to even say into a simple step-by-step building project. So, we've just gone through two completely different versions of the same question. One was about seesaws and graphs. The other was about rust and color. So what's the big takeaway from all this? Well, it turns out they weren't just abstract puzzles. They were testing the same huge fundamental ideas. Question 6a taught us that reactions are this dynamic dance, always looking for balance. And question 6b showed us that rust is just an invisible war over electrons, and that a molecule's beautiful color is decided by where those very same electrons are allowed to live. This whole tale of two questions really shows you that chemistry isn't just about formulas in a textbook. It's the invisible architect of our entire world. So the next time you see the perfect shimmer on a car or a rusty old chain on a fence, you're looking at the results of that same silent war for electrons and that same delicate dance of equilibrium. It just goes to show you, a single question on an exam can hold the keys to understanding everything around us. Makes you wonder, what other secrets are just waiting to be explained?